this video, let's just do a very quick review of some of the essential material of calculus. Now, in addition to calculus, in order to succeed in this course, you're of course going to need to know the material pre-calculus very well, in particular trigonometry. So I'm expecting you to know the Pythagorean identity as well as the different values that you get from the unit circle. In addition to that, with regards to derivatives, you're going to definitely need to know how to calculate the derivatives of a variety of different functions. You're going to need to know how to use those rules, power rule, product rule, chain rule, etc., in combination with the formulas for the derivatives of the basic functions, such as natural log, sine, cosine, and e. We're also going to need some information about limits, especially in the first half of the course. For limits, the stuff that's really important is limits at infinity for rational functions, limits as x goes toward infinity, as well as L'Hopital's rule. And in addition to that, we're going to need to know how to integrate stuff. So how to find the antiderivatives of the basic functions, how to actually do partial fraction decomposition, as well as how to do some fundamental integration techniques such as U sub and integration by parts. Now, just a heads up, this is a really quick review, and I cannot possibly go into detail about all of these because this is the material of like 2 quarters. So we're just going to go over it in very shallow basic terms to refresh your memory. If you need any additional resources, feel free to reach out to me and I can share with you some open source textbooks as well as some videos that are available online. Derivatives. So let's recall that the derivative rules were as follows. We had the power rule, which told us how to take the derivative of a quantity like x to the power whatever. That power just comes down and then you decrease the power by 1. We also had the sum difference rule. Derivatives play really well with sums and differences. If you want the derivative of f plus or minus g, take those derivatives separately and then add or subtract the results. Same thing with constant multiple rule. You can basically just ignore the constant and take the derivative of the function by itself. Now, when it got to things like products and quotients, the formulas became a lot more complicated. In order to calculate the derivative of a product, you could not calculate the derivative of f and g and just multiply the results together. It was more complicated than that. We had the derivative of the first times the second plus the first times the derivative of the second. And for quotients it was even more complicated. Bottom times the derivative of the top minus top times the derivative of the bottom all over bottom squared. Chain rule is one of the more infamous rules in terms of how easy it is to use incorrectly. If you want to take the derivative of a function with another function plugged into it, you have to take the derivative of the outer function and then multiply it by the derivative of the inner function. Let's find a derivative of the fraction. Note that this square root of x term is equivalent to x to the power 1 over 2. So when we find the derivative of this, that can be found using the power rule. Now we have a quotient here. So quotient rule tells us to take the bottom, 2x to the 5th power plus x to the 4th power plus 1, and multiply that by the derivative of the numerator. The derivative being take the power, pull it down, and then decrease the power by 1 unit. Then we subtract the numerator, square root x, and multiply that by the derivative of the denominator. So 2x to the 5th power, 5 comes down, and I get 10x to the 4th power. X to the 4 comes down, and I get 4x cubed, and the derivative of a constant, the derivative of 1, becomes 0 and vanishes. This all over the denominator squared. Now we also had the derivatives of some basic functions. We had the natural log function, whose derivative was 1 over x. The exponential function, which was really unique because it was equal to its own derivative. And then the trig functions. The derivative of sine was positive cos, but the derivative of cos was negative sine. So let's use that together with the chain rule to find the derivative of the following. Not e to the power x, but in x's place, the function cos x has been placed there. This is a perfect opportunity to use chain rule. It says take the derivative of the outer function, e, but the exponential's derivative is just equal to itself, and then multiply that by the derivative of the function that has been plugged into e, in our case cos. And the derivative of cos is negative sine. For another example, one that actually is going to come up quite often in our work, suppose we wanted the derivative of cosine of 3x, say. I would take the derivative of the outer function, cosine, result negative sine, and multiply that by the derivative of the inner function, 3x. So this is equal to negative 3 sine 3x. Now the next bit of information that we're going to need is how to calculate limits of rational functions. For example, something like 5x to the third power plus 1 over 4x to the fourth power plus 1. Now the nice thing about rational functions, which is a polynomial divided by a polynomial, is that as x goes to infinity, their behavior is completely dominated and controlled by the leading terms. Those are the terms that have the highest exponent. So as x goes to infinity, this first fraction, for example, is completely controlled by the behavior of the leading term 5x cubed over 4x to the fourth power. When x is really large, the plus 1 doesn't have much impact. So this can be simplified to 5 over 4x to the first power, which goes to 0 as x goes to infinity. Likewise for this second one, which is almost the same, except we have an x to the third in the denominator as well. And we have 5x cubed, 4x cubed, which is 5 over 4. And that number is the limit as x goes to infinity of the second fraction. Now, the rule given above for rational functions is a special case of a more general rule, which is called L'Hopital's rule, which is telling you a way, a shortcut for calculating the limit, not the derivative of a ratio. That's covered by quotient rule, but the limit of f of x divided by g of x. It says that if both your numerator and denominator go to 0 as x goes to infinity, or if both of them go to infinity as x goes to infinity, then you can find the limit of the ratio by finding the limit of the ratio of the derivatives, f prime divided by g prime. For example, we have here e to the x divided by x squared. As x goes to infinity, both the numerator and the denominator go to infinity. So L'Hopital's rule says that if you want the limit of e to the x divided by x squared, you could just as easily calculate the limit of the derivative of e to the x divided by the derivative of x squared. And since both the numerator e to the x and the denominator 2x still go to infinity, you can take the derivative even one more time. Take the limit as x goes to infinity of e to the x over 2. And now, because the numerator is getting infinitely large and the denominator is constant, this limit is equal to positive infinity. Now when it comes to integration, we also have a set of standard formulas. We have the formulas for the antiderivative of most power functions. If you're taking the antiderivative of x to the nth power, where that exponent is anything other than minus 1, then increase the exponent by 1 and then divide by the increased exponent and add this unknown arbitrary coefficient. In the special case that that exponent was -1, then the antiderivative becomes natural log of absolute value of x plus c. The integrals of the trig functions behaved similarly to the derivatives, except the signs behaved in the opposite way. The integral of cos is positive sine. The integral of sine is negative cos. An exponential function is unaffected by antiderivatives, same as for derivatives. Integral of e to the x is equal to e to the x plus c. Now I would review u sub and integration by parts here, but I think it's simply too complicated. If you're interested in an example of that and a review of how u substitution works, please talk to me in office hours or send me an email and I can hook you up with some additional resources and videos. However, what I do want to talk about is something called partial fraction decomposition, which was taught in Calculus 2, but we will be using for a different purpose here, and you will be using again if you take 238, which we call differential equations. And I'm going to teach you a shortcut method, which is called the Heaviside cover-up method. This can be used only in a very specific case, which is when your fraction's denominator has linear factors that don't have any exponents that are larger than 1. So this method that I'm about to show you could not be used on a fraction which had x squared plus 1 in the denominator, because x squared plus 1 isn't linear. It also could not be used on a fraction with something like x minus 2 to the quantity 2 in the denominator, because that exponent of 2 is too large. Where can this be used? Let's try and find the partial fraction decomposition of 1 over x squared plus 5x plus 6. So to begin with, let's factor the denominator. X squared plus 5x plus 6 splits as x plus 2, x plus 3. And we're trying to split it as 1 something over x plus 2 plus something over x plus 3. Now the question is, what goes in each of these numerators? Now you can figure this out by clearing the fractions and solving a system of equations for a and b. But the shortcut that I'm about to show you, the Heaviside cover-up method, says to find a, which is above x plus 2. On the left side, cover up the factor x plus 2 and plug in x equals the opposite, -2. So this is called the Heaviside cover-up method because we're plugging into the left side, which is heavier or weightier. The fraction there is larger than the fractions on the right. And it's called the cover-up method because you cover up the factor that corresponds to the number that you're trying to find. So I'm going to cover up mentally. I'm going to cover up x plus 2, and I'm going to plug in x equals -2 to what's left, 1 over x plus 3. So 1 over -2 plus 3 is equal to 1 over 1. That's the value of a. For b, it's very similar. For b, which is above x plus 3, cover the x plus 3 on the left and plug in the x equals -3. That's the opposite of that quantity. So on the left side we have 1 over x equals -3 plugged into the x plus 2 that remains when x plus 3 is covered. That's equal to 1 over -1, and that's b. So what's the partial fraction decomposition? It's equal to +1 over x plus 2 plus -1 over x plus 3. So that's the review, a very, very quick and shallow review of all the information that we need from Calculus 1 and 2 to really succeed in this class. If you're rusty at all in terms of the calculation of derivatives, in particular the use of chain rule, that is something that you're going to want to sort out early, because we will need that information, and I'm going to work through the example problems as if you know how to do that already. Similarly for the Calculus 2 material, when I'm going through and I'm calculating antiderivatives, I'm going to work at such a pace that assumes that you already know how to calculate integrals. I'm going to show you as much work as I expect from you on an exam, but the explanations may move a little quickly. But if you're confused at all about how to do the calculus calculations, please feel free to contact me and ask me questions in office hours. I'm more than happy to clear up any questions that you might have.